We're working with a dataset that has two distinct groups, or clusters, of data points. Think of it like sorting marbles. You have a bunch of red marbles and a bunch of blue marbles, and we're trying to figure out where each marble belongs. These numbers represent the centers of our two clusters. The first cluster is centered around the point 1, 2, and the second is centered around 5, 6. Imagine these points as the average location of each marble group. Covariance describes how spread out each cluster is. A larger covariance means the points are more scattered. Here, we have two covariance matrices, one for each cluster. The first cluster has a smaller covariance. Its points are tightly clustered around 1, 2. The second is more spread out around 5, 6. The zeros show the directions of spread do not correlate. These weights show the probability of a data point belonging to each cluster. The first cluster has a 60% chance, while the second has a 40% chance. Think of it like a weighted coin flip. The coin is more likely to land on one side than the other. Yes, because the weight for the cluster centered at 1, 2 is 0.6, it's more likely for a data point to belong to that cluster than the other cluster which has 0.4. Absolutely, the covariance matrix for the cluster at 5, 6 has larger values than the covariance matrix for the cluster at 1, 2, meaning it's more spread out. Correct. The model assumes that each data point within each cluster is independent of each other, like rolling multiple dice. Each roll doesn't affect the others. The GaussianMixture model, GMM, is a statistical model that assumes your data is made up of several Gaussian distributions, bell curves. In this case, we're dealing with a model that identifies two of them. Nope. The covariances show different spreads, variances, for our two clusters. The spread of the points in one group is different than the spread of points in the other group. Statement B is true because of the weights assigned to each cluster. The cluster at 1, 2 has a greater probability due to its larger weight. Statement C is true because the values in the covariance matrix for cluster 5, 6 are larger, indicating greater spread or variance. Statement D is true because GMMs are built on the assumption of independence of data points within each of the identified clusters. I see that option A claims the variances are equal. Looking at the covariances, I see that the first cluster has a variance of 1, and the second cluster has a variance of 2. They're not equal, so this statement is false. Here, option B suggests the cluster centered at 1, 2 has a higher probability. The weights given are 0.6 and 0.4. The higher weight, 0.6, belongs to the cluster at 1, 2, making this statement true. Option C states the cluster at 5, 6 has a larger covariance. Looking at the covariance matrices, the one for the 5, 6 cluster is 2, 0, 0, 2, while the other is 1, 0, 0, 1. Clearly, the former has a larger variance, making this true. Covariance matrices show how much the variables spread out together. Think of it like this: the bigger the number in the matrix, the more spread out the data is. Finally, option D suggests the data points within each cluster are independent. This is a standard assumption of Gaussian mixture models. So, option D is true. This is just a summary instruction of the question. Based on our analysis, we can confidently select options B, C, and D. This question tests my understanding of a Gaussian mixture model, a powerful tool for clustering data. I will use my knowledge of this model to analyze a specific example. The dataset has two distinct, separate groups of data points. Thinking of it like sorting colored candies, two distinct colors. The Gaussian mixture model is being used to find these two separate groups in the data, and it's assumed each group follows a bell curve shape, Gaussian distribution. I'm telling the model to find exactly two clusters. This is like specifying that I only want to find two colors of candies. N underscore components is simply the number of clusters. These are the results after the model has been applied to the data. I'll look at the means, covariances, and weights to understand the clusters. These are the central points, means, of my two clusters. One cluster is centered around the point 1, 2, and the other around 5, 6. Imagine these are the average locations of two different groups of candy. These matrices describe how spread out the data is within each cluster. The numbers along the diagonal represent the variance in each direction. Think of the spread of the candies. Larger numbers mean more spread out data. Both matrices are diagonal, indicating that the features are uncorrelated within each cluster. These represent the probability that a randomly chosen data point belongs to each cluster. The first cluster has a 60% chance of containing a random data point, while the second cluster has a 40% chance. Think of this as the relative abundance of each candy color. I need to evaluate each statement based on the model attributes. I examine if the variances, spread, within each cluster are the same. I'll check if the cluster centered at 1, 2, has a higher probability, weight, than the cluster at 5, 6. I'll compare the covariance matrices to see if the cluster at 5, 6, has a larger spread, covariance. This checks if my model assumes that data points within each cluster are independent of each other. That's a pretty standard assumption for Gaussian mixtures. I'm working with a dataset that clearly shows two separate groups of data points. Think of it like two distinct clouds of points on a scatter plot. I'm using a powerful tool from the Sklearn library called GaussianMixture. This helps me model my data as a mix of Gaussian distributions, bell curves. I've told the GaussianMixture model that I expect to find two separate bell curves within my data. This is because I already know there are two distinct clusters. These are the center points of my two bell curves. The first is located at coordinates 1, 2, and the second at 5, 6. Imagine them as the peaks of my bell curves. These numbers describe how spread out each bell curve is. The first curve is less spread out and the second is more spread out. Notice that the off-diagonal elements are 0, meaning the x and y directions of the spread are independent. These tell me the relative likelihood of a data point belonging to each bell curve. The first bell curve is 60% likely and the second is 40% likely. Because the weight for the 1, 2 cluster is 0.6, 60%, it's more probable to sample a point from that cluster than from the 5, 6 cluster. The covariance of the second cluster, at 5, 6, is 2, 0, 0, 2, which is larger than the first cluster's covariance, indicating a greater spread. The Gaussian mixture model assumes that the data points within each cluster are independent of each other. This is a key assumption of the model. This is a multiple-choice question testing your understanding of the Gaussian mixture model, a powerful tool in machine learning used to group data points into clusters that follow Gaussian distributions. Think of it like sorting different colored marbles into groups based on their color distribution. The dataset we're dealing with has two very distinct clusters of data points. Imagine two separate piles of marbles, clearly distinguishable from each other. These are the center points of the two clusters. The first cluster's center is at coordinates 1, 2, and the second is at 5, 6. Think of these as the average location of the marbles within each pile. These numbers describe how spread out the data points are within each cluster. A larger number means a wider spread. The covariance matrices are diagonal, which means the data points x and y coordinates within each cluster are independent of each other. The first cluster has smaller variance than the second, implying that the data points in the first cluster are more tightly clustered around 1, 2, than the second cluster around 5, 6. These represent the probability of a data point belonging to each cluster. The model thinks there's a 60% chance a random data point will belong to the first cluster and a 40% chance it will belong to the second cluster. I look at the weights. The higher weight, 0.6, is assigned to the cluster centered at 1, 2. So, yes, the model is more likely to assign a new data point to this cluster. I compare the covariance matrices. The second cluster's covariance matrix has larger values, 2, compared to the first cluster, 1. Therefore, the data points in the second cluster are more spread out. The Gaussian mixture model assumes that data points within each cluster are independent. This means the location of one data point doesn't influence the location of another within the same cluster. It's a key assumption. The covariances show different variances for the two clusters. Therefore the answer is false. I'm going to evaluate each statement about the Gaussian mixture model using the information given. Means, covariances, and weights. We'll see which statements match what the model tells us. Let's get started. This statement is false. I see that the covariances are different. One cluster has a covariance matrix of 1, 0, 0, 1, representing variance of 1 in both directions, while the other is 2, 0, 0, 2, showing a variance of 2 in both directions. Therefore, the variances are not equal. This is true. The cluster centered at 5.0, 6.0, has a covariance matrix with larger values, 2, compared to the cluster at 1.0, 2.0, which has a value of 1. A larger covariance indicates more spread or variability in the data points around that cluster's center. Correct. The weights are 0.6 and 0.4. The higher weight, 0.6, is assigned to the cluster centered at 1.0, 2.0, indicating a higher probability of a data point belonging to this cluster. This is a fundamental assumption of Gaussian mixture models. I see that the model assumes each data point within a given cluster is independent of other data points in the same cluster. This question tests your understanding of Gaussian mixture models. I'll explain what a GMM is and how we use its parts to answer questions. It's a statistical model that assumes your data comes from a mix of several Gaussian distributions, which are like bell curves. The dataset has points that seem to group into two clusters. We can model this with a Gaussian mixture model using two Gaussian distributions, because of the two clusters. These are the centers of our two bell curves. One center is at 1, 2, and the other is at 5, 6. Think of them as the average location of data points within each cluster. This shows how spread out the data is around each center. The first cluster, 1, 2, has a covariance of 1, 0, 0, 1. The second one, 5, 6, has 2, 0, 0, 2. The higher the numbers, the more spread out the data points are. These show how likely it is that a data point belongs to each cluster. The first cluster, at 1, 2, has a 60% chance of containing a random data point, while the second cluster, at 5, 6, has a 40% chance. You need to use the information from the means, covariances and weights to determine which statements are true. This asks if the two clusters have the same spread, covariance. Looking at the covariances, I see they are different, so this is false. Nope. This asks if there's a higher chance a data point belongs to the cluster centered at 1, 2. Since the weight is 0.6, 60%, compared to 0.4, 40%, the answer is true. This asks if the data in cluster 5, 6 is more spread out. The covariance of 5, 6 is 2, 0, 0, 2, which is larger than the covariance of 1, 2, which is 1, 0, 0, 1. Thus, this is true. GMMs assume that points within each cluster are independent, they don't influence each other. This is a core assumption of the model, so this is true.